Let's jump right into this explainer. Today, we're taking a pretty fascinating journey straight through the heart of calculus. We're exploring a critical chapter that perfectly bridges the gap between basic algebra and those more advanced functions. We're looking at continuity and differentiation, basically taking these ideas from abstract concepts all the way down to concrete calculations.
So we start with this really brilliant observation from Albert Einstein, and it's a fantastic anchor for our discussion today. Often when we look at pages of complex calculus formulas, it kind of looks like an alien language, right? But Einstein reminds us that these concepts are, actually, just tools. They're mathematical refinements of our everyday intuition. We already understand the physical concepts of motion, smoothness, and connection. Calculus just gives us the language to measure them precisely.
And speaking of refining everyday thinking, that brings us right to Sir Isaac Newton. Thinking about him really establishes the historical weight of the monumental math we're about to explore. Newton looked at the motion of the planets, the falling of objects, and he realized that standard algebra just wasn't enough to capture things that are constantly changing. He needed a completely new system, a refinement of thought, and that actually led to the foundations of the calculus we use today.
Now, because math builds strictly upon itself, step by step, here's our roadmap for the explainer today. We've got refined everyday thinking, the Penlift test, defining differentiability, exponentials and logarithms, and finally, the advanced calculus toolkit.
Moving right along to Section 2, the Penlift test.
Let's look at our first major concept, which is continuity, and see how it builds from a very simple visual idea. If you want an intuitive, everyday grasp of mathematical continuity, just ask yourself this simple question when you're looking at a curve. Can you trace the entire line on the paper without ever lifting your pen? If the answer is yes, you're looking at a continuous function. But if there's a hole, or a jump, or a break that forces your pen off the page, well, it's discontinuous. It's really that wonderfully simple at a visual level.
Okay, so the crucial point here is how we translate that visual Penlift test into rigorous mathematics. To pass the test mathematically at any specific point, let's just call it C, three things must happen. Our approach from the left side, our approach from the right side, and the exact actual destination point must perfectly align. If they all equal the exact same number, boom, the path is connected.
When we compare that left-hand limit with the right-hand limit, we're essentially checking if the two sides of the road actually meet up. Any mismatch here means your pen absolutely has to lift. Think about it. If the left side is heading toward a value of 1, but the right side is heading toward a value of 2, you've got a disconnected jump or a gap in your graph. Basically, the bridge is broken.
And this brilliantly illustrates the concept of infinity, which, let's be honest, often trips people up when looking at limits. Take the function 1 divided by x. As our x values step closer and closer to 0, going from 0.1 to 0.01 to 0.001, the outcome mechanically explodes from 10 to 100 to 1,000. It's pretty wild, but it proves infinity isn't some magic number. It's simply a mathematical consequence. It's a direction of relentless growth as we approach a boundary where the function just isn't defined.
All right, on to Section 3, defining differentiation.
So now that we understand how to mathematically guarantee a continuous, unbroken line, we really need to ask our next big question. How do we find the exact slope or rate of change at any given point on that line? Well, this brings us to differentiation. To be differentiable, the graph must not only be continuous, it has to be smooth. That formula calculates the rate of change by shrinking the distance between 2 points until it's virtually 0. But here's the catch. You can't find the derivative at a sharp, jagged corner. Even if you never lifted your pen to draw a harsh zigzag, that sudden violent change in direction means there's no single definable slope right at that sharp point. Simply put, differentiation requires smoothness.
Now, once we know a function is smooth and differentiable, thankfully we don't use that long limit formula every single time. We use standard derivative rules. And hey, don't get overwhelmed by the memorization here. Just think of these standard rules as foundational blueprints for decoding the geometry of motion. For example, if you know your position is following a sine wave, this blueprint tells you your velocity is mapping out a cosine wave. Pretty cool, right?
Which brings us to Section 4, exponentials and logarithms.
Let's upgrade our toolset a bit and introduce a fascinating new class of functions that govern incredible, compounding rates of growth. Now, what's really interesting about exponential functions is how they behave. Unlike polynomials, where the variable is the base, here the variable is literally in the power. Functions using the natural base e map out curves that grow steeper and faster than any basic polynomial ever could. Basically, the larger the x gets, the faster the function itself accelerates upward. It's explosive. And as with most things, wherever there is a powerful mathematical action, there's an equally powerful reaction. Logarithms act to precisely undo exponentials. They essentially tell us what power we need to raise a base to in order to get a specific number. If basey exponentials are used, their counterparts are called natural logarithms, which you'll often see denoted simply as ln x in equations.
I absolutely love this symmetrical storytelling. The exponential and logarithmic functions are quite literally mathematical reflections of one another. Every single property is neatly flipped. The domain and range, swapped. Where the exponential rides along the x-axis, the logarithm tightly hugs the y-axis. If you could fold a graph right down the diagonal line of y equals x, the e to the x curve and the natural log curve will kiss perfectly. They are literally two sides of the exact same mathematical coin. And finally, Section 5, the Advanced Calculus Toolkit.
Okay, let's assemble everything we've learned so far, the continuity, the rules of differentiation, and our new exponential and log functions, and put them into a power user toolkit for solving complex multivariable puzzles. First up in the toolkit is parametric differentiation. You see, sometimes x and y aren't directly talking to each other. Instead, they're indirectly linked by a third variable, like time, which we usually just call t. Parametric differentiation gives us this incredibly easy, logical three-step procedure. We just find the rate of change for x over time, find the rate of change for y over time, and then we simply divide them to find the overall slope of the actual path.
Next up, we have logarithmic differentiation. Imagine a total nightmare scenario where a function with an x is raised to the power of another function with an x. Standard rules completely fail here, but by taking the logarithm of both sides first, we can leverage the properties of logs to drop those difficult exponents right down into simple multiplication. Seriously, it acts exactly like a mathematical cheat code, completely turning an impossible differentiation problem into a perfectly standard product rule equation. Finally, we reach the second-order derivative. We've spent all this time figuring out how to find the derivative, which, as we know, is the rate of change. But what if that rate is also changing? Think about it. If we take our derivative and differentiate it a second time, we get the second-order derivative. We're effectively moving our understanding a whole layer deeper into the mechanics of the system. And that leads us perfectly to our final thought for this explainer. If a first-order derivative gives us the speed of a moving object, the second-order derivative tells us if that object is accelerating or hitting the brakes. It predicts the change of the change. We've built an incredible mathematical toolkit today, going from simple continuous lines all the way to complex rates of acceleration. And it leaves us to wonder, how will you use these tools to solve the universe's geometric puzzles? Thanks for joining me on this one, and keep exploring.